So hello students, we'll continue again with unit number 2 and topic number 5, which is networks, preparation of CPM networks and activity of link and node. So network, type of precedence relationships, a strategy for scheduling activities in a project plan. The precedence diagramming method, that is PDM, is a strategy for developing a project schedule network diagram that utilizes nodes to represent activities and associates them with projectiles that illustrate the dependencies. This method is likewise called the activity on node, that is AON. So this is figures your precedence relationship. That is, you start from the left, A, B, C, D, E, and you finish on the right. From the left to the right, on the left side you have to write the lowest level of the work starting, and finish, that will be I think on the D, E. E is the last node. On E you have to write the final outcome of the project, that is finished. So the most significant advantage of using the precedence diagramming method PDM is that it quickly allows the project team to understand all the program the schedule activities, and it affiliates and coordinates with each other. From A to E, that is, we have to run it from left to right, from A to E. At first A will be the lowest level, and likewise you have to write it down, or you have to note down your work. This, how you will know that which is the lowest and which is the highest level. This thing you have to deduct it or take it down from the work breakdown structure, which you have to make it or plan it first. After that, after making the work breakdown structure, then only you can go for the precedence diagramming method. So as a project manager, ensure that your emphasis is on project sequence as you put effort on the activities. You may have come across additional tasks that have to be performed, and henceforth you can incorporate the equivalent in the precedence diagram and to work breakdown structure. So at last, draw the bows between the assignments that connect up and ensure that there aren't any tasks sitting isolated or being left out. As you can see here in this precedence relationship, from the start you can see on the left is the clear site. First step is you have to clear site, you have to dig trenches, and you have to lay foundation. And while doing the clear site and dig trenches, simultaneously what you have to do, you can buy bricks, you have to prepare the bricks, and then you have to prepare the cement. So after laying the foundation, as you can see, you can go and prepare the cement. In both ways you can do. After preparing bricks also you can prepare cement. After laying the foundation also you can prepare your cement. Cement comes in between. So when after preparing cement you go to lay the bricks, and that is the end. So this is an example of precedence, how a precedence relationship is done. So types of precedence diagramming method relationship. The significant output in the sequence activities process is the network diagram amidst the sequence activities process. The activities that are explained in the defined activities process is sequence of specific activities that rely upon each other. While the network diagram shows the project activities and presents the interrelationships of activities, the precedence diagram method PDM is the most widely recognized strategy to draw network diagrams. So it is normal for certain affiliates and dependencies between the activities in precedence diagramming method. With the PDM method, 4 types of relationships are used in the activities to complete the network diagram of a project, and they are, here you can see, start to start, start to finish, finish to start, and finish to finish. So these are the types of precedence diagramming method relationships. First one, finish to start, that is F to S, is the most common dependency type used between activities. Activity can't begin before a predecessor activity completes. Before the earlier activity completes, you can't start a new activity. So at that point, a finish to start dependency needs to be present between these two exercises. Next, start to start, that is S to S. S to S is a kind of dependency, shows that two activities determined to start together. They start parallelly. Finish to finish, F to F, in a project illustrates the two activities in a project determined to finish together. That is, two activities in a project, they finish with together, that is, they finish parallelly. Next, start to finish, S and F, is a unique type of dependency on projects. It can be utilized instantly along with its supply chain materials. For instance, in this type of dependency, activity B can finish only after activity A starts. Preparation of CPM networks. So project scheduling by PERT or CPM consists of four main steps. Number one, planning. In underneath planning, the planning phase is started by splitting the total project into small projects. The smaller projects in turn are divided into activities and are analyzed by the department or section. Relationship of each activity with respect to other activities are defined and established, and the corresponding responsibilities and the authority are also stated. Thus, the possibility of overlooking any task necessary for the completion of the project is reduced substantially. Through scheduling, that is planning, the ultimate objective of the planning phase is to prepare a time chart showing the start and finish times for each activity, as we mentioned earlier, as well as its relationship to other activities of the project. This also we have mentioned it earlier, explained to you earlier. So moreover, the schedule must pinpoint the critical path activities which require special attention if the project is to be completed in time. For non-critical activities, the schedule must show the amount of slack or float times which can be used advantageously when such activities are delayed or when limited resources are to be utilized effectively. 3. Allocation of resources. Allocation of resources is performed to achieve the desired objective. A resource is a physical variable such as labor, finance, equipment, and space which will impose the limitations of the time of the project. So when resources are limited and conflicting with each other, demands are made for the same type of resources, and a systematic method for allocation of resources becomes essential. Number 3, resource allocation usually incurs a compromise, and the choice of this compromise depends on the judgment of the managers. 4. Controlling. The final phase in project management is controlling. Critical path methods facilitate the application of the principle of management by expectation to identify areas that are critical to the completion of the project. By having progress reports from time to time and updating the network continuously, a better financial as well as technical control over the project is exercised. Road diagrams and time charts are used for making periodic progress reports. If required, a new course of action is determined for the remaining portion of the project. Next topic, activity on link and activity on node representation. The first one, activity. An individual operation which utilizes resources and has an end and a beginning is called activity. An arrow is commonly used to represent an activity with its head indicating the direction of progress in the project. These are classified into four categories: predecessor activity, successor activity, concurrent activity, and the fourth one is in the next slide. So the first one is predecessor activity. Activities that must be completed immediately prior to the start of another activity are called predecessor activities. Second, successor activity. Activities that cannot be started until one or more of other activities are completed but immediately succeed them are called successor activities. 3. Concurrent activity. And activities which can be accomplished concurrently are known as concurrent activities. It may be noted that an activity can be predecessor or a successor to an event, or it may be concurrent with one or more of the other activities. This predecessor successor concurrent distinct, it is the same as we have discussed earlier in this previous slides. Finish to start, start to finish is the same, almost same. Fourth, dummy activity. An activity which does not consume any kind of resource but merely depicts the technological dependence is called a dummy activity. The dummy activity is inserted in the network to clarify the activity pattern in the following two situations: to make activities with common starting and finishing points distinguishable, to identify and maintain the proper precedence relationship between activities that is not connected by events. For example, you consider a situation, look at the figure also when I say it. For example, consider a situation where A and B are concurrent activities. C is dependent on A, and D is dependent on A and B both. Such a situation can be handled by using a dummy activity as shown in the figure. That's all for this lecture. You can give your name, enrollment ID in the chat box for your attendance, and also at the same time we'll go through videos. Thank you.
In scheduling. So far, what we have said is that the time of completion of an activity is firm. That is, it's a given number. And then we have constructed networks to determine project completion times based on interdependencies. So you would recall that in a first example, when we said there was 500 man days involved, then we divided this by 10, which was the number of people, and came up with 50 days of activity time. And then we have also constructed in the last class a slightly different network, a more elaborate network, and illustrated the concept of critical path. That is that path which needs to be monitored more regularly, more continuously than the others, and no slippage can be allowed. But in any case, when the interdependencies were taken into account, the time associated was taken to be firm. An activity ij, it was known this will be completed in a time of tij. Now today, what we will do is, we'll take a slightly different look at the activity duration. That is, this tij with the emphasis of incorporating the element of uncertainty. How do you incorporate a situation when the tij is not a firm number, but more like a probability distribution? An activity may be completed in 10 days, but it might spill over to 12 days. If something good happens, if we are lucky, then it might be completed in just 5 to 6 days. So this idea that the time associated with each activity is not necessarily a fixed number, that is something which we will focus on today in our discussion. So, how do we actually go about estimating the times for the different activities? One simple approach is to keep records that will give us the average durations. So, a construction company keeps a record for erection of trusses and so on, and finds out that, okay, in different projects, what is the kind of time that it takes? And from there, we try to find out the productivities and then try to map that into a new project and try to estimate the time involved for that project. We have talked about in the initial part of this course that each construction project is really unique. So the bridge built at a particular place is surely different from maybe a similar bridge but built elsewhere. Also, the productivity of labor during the course of the project changes, and that could also affect the duration of activities. So if there's an activity, you put a gang of labor or a certain set of workers, on day one, they may not be able to produce the maximum output. But as they learn the activity, as they learn their role in the whole process, their productivity improves. So how do we keep track of these kind of things? Going back to the basics, usually the duration dij of an activity is determined using this formula, which is aij upon pij multiplied by nij, where ij is the activity that we are talking about. Aij is the required amount of work. Pij is the productivity of the person, which could possibly take care of the learning curve and so on. And Nij is the number of persons working on that job independently and together. So with this, we can find out the Dij. But each of these parameters has their own variations. For example, as far as Aij is concerned, the only estimate which we can make from is the good for construction drawings. It might happen that there will be some changes in the total amount of work at site. Whether it is paid for or not, it doesn't matter, but the fact is that if additional work is carried out or less work is carried out, then it will affect the time duration. So coming to the next part, which is labor productivity, this could also be an important aspect of determining the total time involved. And that is where the learning curve becomes important. So what is the learning curve? A general understanding of the productivity rates can be obtained from the concept of learning curve. And the basis of the learning curve lies in the fact that as crew becomes familiar with the activity and the work habits, their productivity tends to improve. Of course, there is a limit beyond which it does not improve. There is a limit to the capacity of each worker. This capacity may be different for different workers, but sure enough, there is a starting point and it goes through a learning phase and a steady phase for each worker. In other words, productivity increases as the crew gains experience, which is possible if sufficient time is available. And most construction projects, that is indeed the case. So now, another thing is the number of workers. This equation here assumes that the duration of an activity is inversely proportional to the number of persons in the crew or the number of workers in the team. But is this assumption absolutely true? Is it true in the absolute sense? If we keep increasing this Nij, is there no limit for the reduction in the duration that we get? There are two reasons why this assumption is not really true. One is the crew may not be able to work independently. In a certain construction site, there is a limit to the number of workers who can be accommodated without interfering with each other's productivity. So that's one part of it. The second thing is coordination between individual tasks has to be ensured. And that also becomes difficult. We all know the saying that too many cooks spoil the broth. So if there are too many people trying to do an activity, that also has an adverse effect on the time duration. Apart from the workers working independently, the coordination between individual tasks and the individual crew members has to be ensured. More persons in the crew may result in the delay in the following situations. An example is design tasks are often divided between architects and engineers, in which greater coordination is required among themselves. In such situations, more the number of people in the crew will obviously affect the coordination, and therefore it affects the time. Ensuring a smooth flow of material or information of any nature may become increasingly difficult if there is more number of people in the crew. Further, in projects which are being executed for the first time, it may not be possible for planners to finalize the exact estimates of the parameters like productivity rates, optimum number of people in the crew. Other considerations may include practical difficulties like the weather, contractors' failure to deliver materials, machinery breakdowns, and so on. Also, most of the activities that are outside the control of the client are certainly uncertain. One simple example could be the time required to get approvals from outside agencies, and that could affect the project in different ways. What this competent authority means is, for example, if there is a project which requires an approval from a pollution control board and such regulatory authorities, that might be not within the control or within the powers of the client to be able to implement. And that introduces an element of uncertainty as far as the completion of the project is concerned. And it's not only the project, but also it has the effect obviously on individual activities, and those individual activities in turn affect the project. This underlines the need to understand that there exists an uncertainty in estimating activity duration, and therefore considering to use continuous probability distribution functions becomes relevant in this case. So what we are saying in this sentence is, instead of assigning a particular time t for any activity, can we not talk in terms of a probability distribution? That is, yes, this activity will take some time, but that time could be maybe a little less, maybe a little more. So whether this distribution should be normal or not is the next question that we need to answer. So without going into the statistics of the whole issue, let's try to understand the basic story of the normal distribution. The normal distribution with values widely spread away from the average is the situation where the standard deviation is high. Compared to this picture here is a situation where the peak is sharper, which means that the area in this part is closer to the mean. If we want to go to the same area here, we will go more standard deviations away from the mean. However, in both cases, the normal distribution is symmetric. So the problem with our construction activities is that they are not necessarily symmetrically distributed. So now, what are the requirements that we need to impose in determining or finding the kind of distribution that helps us say that, yes, this is what really meets our requirements? The probability of reaching the most optimistic time, which is early completion, should be very less. So this is a situation where we become lucky and we are able to achieve the target very quickly. The probability of reaching the most pessimistic time should be very less. That is, there should be a time where we will definitely be able to complete the project under most adverse conditions. Then there exists only one most likely time which would be free to move between these two extreme conditions. So what we are saying is that there is an optimistic time T0 and there is a pessimistic time Tp. Between this T0 and Tp, we want to define a distribution which is not normal. So either this most likely time will move towards the left, in which case the pessimistic time becomes an outlier, or it will move towards the right, in which case the optimistic time becomes an outlier. So this amount of uncertainty should also be measurable. So once we understand these requirements, we find that the beta distribution that is used in statistics satisfies these requirements for us. So we can use the properties of the beta distribution and move forward as far as determining the expected times of the activities and so on is concerned. So now what is a beta distribution? We assume that this is the most likely time, this is the pessimistic time, and this is the optimistic time, and this distribution is skewed to the right. In this case, however, on the figure on the right, for the most likely time, the distribution is skewed to the left. So this is a situation where most of the times we will be able to complete the project here, except if we become very lucky, we might hit the jackpot and come somewhere here. In this case, we will probably be able to complete the project somewhere here, and only if we are not running in luck at all, we will be able to complete the project within the pessimistic time. So this is the kind of thought process, and we move forward and try to see how the uncertainty in estimating activity times can now be incorporated in a scheduling process like PERT. PERT is the Program Evaluation and Review Technique, and the uncertainty in estimating the duration of an activity is considered in this technique as against the critical path method that we saw in the last class, where the activities had a firm time of completion. It's more suitable to control jobs that have not been done before and there is more uncertainty in the activities. PERT assumes the three estimates of time are random variables satisfying a beta distribution function. So this is what we have been talking about, and now let's try to see how we actually implement it on ground as far as activities are concerned. So we have been talking of an activity ij all the time. So here also we are saying that there's an activity I and j, and we are talking of 3 times associated with it. Optimistic time TO, which is the shortest possible time of completing the activity under ideal conditions. The most likely time TM, which is the best guess of the time required to complete the activity, and the pessimistic time TP, which is the maximum time required to complete this activity. So usually the notation followed is given here. For an activity ij, we give TO, TP, and TM. Now from here, the expected time for completion and the standard deviation in the activity. We know the TO, TP, and TM. Then how do we calculate the T expected of the activity or for the activity ij? Now this is calculated using this equation, that is TO plus TP plus 4 times TM divided by 6. So I'm not getting into the derivation of this. What it really says is that these are the pessimistic and optimistic times, and we are giving a higher weightage to the most likely time, and we are getting an estimate of the time at which or during which this activity will be completed. Please remember that this expected time does not mean or does not give you an idea of the 50% time of completion. This time does not mean that the activity will be completed 50% of the time. That would happen if the time of completion of that activity was normally distributed. Given that it is not normally distributed, TE does not conform to a 50% probability of completion of that activity. Continuing, the variance, that is ST square, associated in estimating the expected time of the activity is evaluated as TP minus T0 divided by 6 squared, and then we must reiterate that TE is taken as a random variable. Moving forward, let's try to implement this thought process in an example. Let's talk of 4 activities A, B, C, and D, and if these were the times that we used in a CPM calculation, that is the firm times. Now, this table here, or this part of the table here, gives you the TO, TP, and the TM for these activities. And the way these TO, TP, and TM have been chosen is to ensure that the time in CPM and the expected time of the activity are taken to be the same. So activity A has 10 here, it is TE here, it is 8 here and 8 here, 15 here, 15 here, and 12 and 12. So this effectively ensures that the TE is the same. Similarly, using this equation here, we've calculated the ST associated with each of these activities. So if we examine this table closely, we find that for activity A, this T0 is a little bit of an outlier. These two times are fairly close to each other, but T0 is the optimistic time. In the case of B, this number here, that is the pessimistic time, is the outlier. And for activity C again, this is the outlier and this is the outlier here. So what we have tried to do through this arrangement of numbers is to convey to you that these activities are not normally distributed, and sometimes they are skewed to the left or they are skewed to the right. And we've already talked before that skewing to the left and skewing to the right has a different meaning when it comes to interpreting the time duration associated with an activity. So now let's actually consider some numbers. Let's consider a network that has two activities, A and B, as shown here. The three estimates for the duration of these activities in days is given on the arrow. So here is the TO, TM, and TP for activity A, which is 1, 2, and TO, TM, and TP for activity B are 6, 14, and 16, which is